So this is experiment, well, it's experiment 3 in 2019, but we'll see how long these videos run. Who knows what number it'll be. It's making of chalcone, so you've got acetophenone reacting with benzaldehyde, a little bit of base, and it does the classic aldol condensation. You call it chalcone or trans chalcone or something like that. Just a quick look at even the TLC. Depending on what solvent you run it in, it might not run quite this fast, but benzaldehyde normally has this lower strip or item, and that is benzoic acid. That's benzaldehyde, acetophenone, and then the reaction ends up having a couple of spots. Leftover benzaldehyde is what it looks like. A lot of people have, in 10-to-1, it runs a bit, these spots are lower down, that's normal. So that's the reaction. So we're going to look at the results. We'll start with the spectra. So benzaldehyde, and you can see this one, there's no peak picking done, should have been done, but it has between 190 and 400. This is basically what it looks like. You see about 3 absorptions, if you will, in the UV spectra. So that's the benzaldehyde. Make sure you have that. Always put the structure on them. Acetophenone looks almost identical or the same, and that's normal. And that hump is around 300. The final product, though, and we already know, we'll discuss this after, it has a very strong, its strong absorption is actually at 309, and you can see it tailing down near 350. If I was to run this much more concentrated, so if these peaks were maxed out up here, you would notice you would still have a small blip right at 400, tails into it, but you have to run it super concentrated. So all that means is there is absorptions happening right around in here, but a low extinction coefficient. But that's exactly what will give it its yellow color, so we'll get to that. Infrared. So acetophenone, always draw the structure. So for this one, you've got a carbonyl, and it's this one, which was not picked. You got to make sure it's picked. It's right around 1710-ish. That's your C double bond O stretch. The overtone, you only circle it if you see it. It's a nice short little spike. If it gets obscured by something else, obviously you don't circle it. These peaks here, and it would have to be the ones over 3000, would be CH stretch, but the C is sp2 hybridized. Next up, we got an aromatic ring. So normally we look right in this 1600, and normally you see sort of like 2 peaks around 1600, and then another one back at 1450. So I mean, you could circle these 3 and call it C double bond C stretch. What this one is here, I'm not 100% sure. I don't bother circling it. Now, whoever ran this one, see how it's only at 750. So this IR is missing. This is an old IR that I happen to have. So basically, when they ran it, yours is normally run down to 450. So there should be a second around 680 or something like that peak here. So normally you see the 2 of them, which is your mono substitute. So if I bring up the benzaldehyde, you'll see exactly what I'm talking about. So here's benzaldehyde. We were talking about the aromatic. We did this the other day, 688, 745. Mono substituted out of plane bending of the aromatic monosubstituted ring. So benzaldehyde, you have the classic Fermi doublet of the CH stretch. Notice this 2737 and 2819, those 2 Fermi doublet for aldehyde CH. These would be your sp2 hybridized carbons with an H stretching. The overtone of the carbonyl stretch, the spike, short little spike. Benzaldehyde C double bond O stretch 1702. The aromatic, and again I would circle these 2 with this 3rd one, C double bond C stretch of the aromatic ring. That's all I would bother with that. Product. Now the product, chalcone, this looks to me like a trace amount of moisture. 30 and 59, that would be your C sp2H stretch of the aromatic ring. This is the classic, only when you see it, the 4 monosubstituted overtones of a monosubstituted ring. 1661. So that's going to be this carbonyl with double resonance. So the C double bond O stretch. 1604, very likely to be the carbon-carbon double bond stretch. And then you're going to see right at 1600 this one here along with this one. You can circle those two, C double one C aromatic ring stretch. And let's see if we have the mono. Yeah, it turns out that it's just like pretty much benzaldehyde. These two would be the mono substituted. And it turns out that you only see two. So that takes care of the IR. Now what I'm going to do is move on to NMR. So what I'm going to do is just draw a quick picture here. I don't have on me any of our 60 megahertz, because last year when our computer died, all the old Spectra died and I didn't have one myself. So what I'll be showing you in a moment is a 300 megahertz NMR. But that being said, right around 7, when you guys run it on ours, the chalcone NMR, if you had super pure product, you would basically get like a lump around 7, and that's if you had pure product, this is all you would see. But a lot of folks end up having out at 10 a little peak, which usually indicates leftover benzaldehyde. So if you see it there, that's what it means. And even somewhere around 2.1-ish, you might see a singlet from the methyl group of acetophenone. So if you've seen a clear signature of acetophenone, a small amount, you see a singlet at roughly 2.1. Benzaldehyde, trace amounts is common. It's the H of benzaldehyde here, but your product, and again, if it was pure on our 60, this is about all you would see, okay? But when you do your reference, I'm just gonna go to, so here's an example of chalcone, and this was actually run on a 500 megahertz machine. So you can see down here at close to 2.1, there's a small singlet, tiny little bit. So, but this is either acetone or a little bit of acetophenone. This is some other stuff that that person had. So this is a clear look on a 500 that resolves the blip I showed you on ours. We're not going to see that. But notice how you're only seeing something between 7.2 and 8 for the most part. Right? This was an expanded blow up of it. So basically for ours, you can circle it and call it aromatic H's. That's about it. The C13, now this is different. I posted this, so this bottom one is the full scale, like 70 to a little over 190. This region is the blow up of this. So up top blows this up. So what I'm gonna do, we know right off the bat that what I've labeled in this picture, number 5, is this peak right there. And in this region of aromatic, which is blown up here, notice how there's 2 stubby short ones, and there's 1, 2, 3, 4 at that height, that medium height, and then there's 4 more up top. So what's interesting is anything that's a quaternary carbon, which is this number 4 and number 3, there's no H's on it, it's these 2 short ones. Up top, it's these 2 short ones. Any of the carbons that has 1 H only, see how number 1 and 2 are duplicated? That's 3, sorry, 3 and 2. But the number 1 here has only 1 hydrogen on it. And then you have number 6 of the double bond, 1 hydrogen, it's sp2, 1 hydrogen, and 1 here. So 1, 6, 7, and 11. What I would do is this one, this one, this one, and this one. Any of these 4 would be 1, 6, 7, or 11. The remaining 2, 3, 9, and 10, which are double and higher, would be these 4. Right? That's how you would assign this. Now, yes, if you ran your carbon 13, your sample was concentrated enough, you would actually see all of these peaks on our instrument. If you don't show all of them, for running your carbon, you get half of if you ran the carbon, but not all of these peaks are showing, it's only missing half a mark for that. So that's basically how that works out. And it looks like that does it for the spectra. Now we go on to the discussion. So the mechanism. The mechanism, this is a classic aldol condensation, which is done in chapter 23 of McMurray. It's a well-known mechanism. This is it, right? So you always include that in discussion. I just came up with an approximate energy level diagram. I chose in the mechanism, we have this anion that might exist for a short period of time, that's intermediate. This is actually an intermediate product that does form for a short period of time. But all of your starting material, this aldol, and final product are very similar in energy. So it doesn't really matter about that too much, but this is approximately what it looks like. So discussion, is this exothermic or not? We don't notice it heating up in particular, but we let it stir for 3 hours, but it gets done. We don't have to heat it, so I would argue that overall, it's not obviously exothermic or endothermic, but if we tried on a large scale, we might see heat coming out or getting cooler, or just do it in a calorimeter. Color, it's a yellow product. So obviously the starting material, which has no color, the energy spacing of pi to pi star is in the UV spectra. After the reaction's done, the extended conjugation, you get more conjugation, makes the pi to pi star gap shrink into the, we would say, visible. When we look at the UV though, and to me that's interesting, I touched on this. When you look at your UV scan, you can say, look, there's nothing here past 400, so how do we know it's absorbing anything in the visible? Well, the fact that it's yellow proves it is. But the pi to pi stars are very, very, very strong absorptions. So all the other ones that are not as allowed are so small, we don't see it yet. See how it's only at 1? If we made this sample much more concentrated, all these here would be way up here and flattened, but as the curve comes down, you would see a blip that tails into 400. And in fact, if I'm not mistaken, yeah, I got it over here. So I'm gonna walk over here to show you exactly what I'm talking about. So on the wall, chalcone. This is what we were looking at. See how it looks flat? I throw in a lot more chalcone, it gets super concentrated, right? And look at, there's a blip right there. Here's 400. So right this small area is what's doing it. So what we can say in our discussion is, look, when you strengthen up your UV visible scan, you can see that the tailing of this does absorb a little bit of the violet. So what's left over for us to see comes out as yellow. TLC and NMR. When you guys run this, as I already pointed out, the TLC indicates a little bit of leftover benzaldehyde or acetophenone, and the NMR can show that if you have that or not, and that's common. And obviously, we would like to check the filtrate as usual if we had an HPLC to run it and find out exactly how much organic material is left in the filtrate. So the only way to get a really good look at the yield. Now, the other thing we can say is there does not appear to be any amount of significant decomposition in this reaction. There's no browning, so it looks like the yield goes pretty good. So that's all we got.